and turn this into the acyclic, going from acyclic to a cyclic conformation, which is important because this actually is happening in biology as well, and to keep the stereochemistry the same in each case. And so we went through this process where we tipped the Fisher projection over. We took this rotation around a bond shown here in this blue, and which is this little loop-de-loop thing here. And then we did the actual reaction, which is a formation of a hemiacetal from a couple days ago here, and that's what's shown here, deprotonating. And then we had to deal with stereochemistry once again because we generated this new chiral center, and we saw that you end up with a mixture of stereoisomers known as anomers in the carbohydrate language. And we needed to come up with an explanation as to why they're not formed in a 50-50 ratio. So we turned to the better depiction of this glucose in this case, and we turned this into the chair conformation, and we reviewed the difference in stability of equatorial versus axial substituents. And so we'll just do this briefly now. One more example of this is that all of this conformational analysis is not limited solely to 6-membered rings, but it also, say, works for a 5-membered ring. So ribose is certainly an important sugar. So we could do the same thing where we could tip ribose on its side. So we'd end up with our aldehyde here. And whoops. So now we have, notice here, these hydroxyl groups, if it's pointing to the right, it's going to be down when we tip the sugar to the side. So we have a hydroxyl group pointing down, and then we start with this species here, where it's the CH2OH. This one is also pointing down. And now, sorry, I should make that bigger. The next one I'll draw much larger. Now what we wanted to do is to rotate around a bond to get this particular hydroxyl group in the right orientation. So we're going to rotate around this bond. We'll just do this little loop to show this. Now let's make it much larger here. All this is the same. Now what we're doing is we're putting this hydroxyl group in the right orientation. Let's draw it like this. So that now we can carry out our formation of the hemiacetal. So we would end up protonating this oxygen here. This hydroxyl group is going to attack. I will skip those steps right now just in the interest of time because that's the same as what we've already seen. So I'll put a couple of arrows in there. And then we're going to end up now, notice what we will do here is we have this carbon of the aldehyde 1, 2, 3, 4, 5. So we have a 5-membered ring, the oxygen. And this is the familiar ring of ribose. Let me try that one more time here. And we would end up having a mixture of stereoisomers as well at the anomeric position. I'll use this little squiggly line to show that we end up with both alpha and beta. And these hydroxyl groups are pointing down as well. Let's just collapse that to the bond line structure. And that gives us the familiar structure of ribose in the closed form. So this idea of converting from the acyclic to the cyclic structure works for all of these carbohydrates. And actually, just like with the glucose, you don't necessarily get a 50-50 mixture of the alpha and the beta anomers. And we can use this to address Paulina's question. So if I scroll back up, I'll come back down to this one in a second. For the glucose, we didn't get a 50-50 mixture of the beta and the alpha, and actually we had the majority of it was the beta. And all we see is the difference here between the two is the orientation of this hydroxyl group that I'm underlining with the pointer, at the anomeric position. And what we notice is in the beta conformation, every group is equatorial. So this is equatorial, as well as all of these other hydroxyl groups, and the CH2OH is equatorial. And the general finding is that the equatorial substituent is more, having a larger group, I should say, at the equatorial position is energetically favorable compared to having it at the axial position. There are exceptions to this. Now in the alpha conformation, all of these groups stay the same, equatorial, so there's no difference there. However, this hydroxyl group at the axial position, at the anomeric position, is now axial. And this is the difference. Equatorial, more favorable with the beta conformation. Axial in the alpha, less favorable. And that's why we don't get a 50-50 mixture. That's why this beta is favored, because it places this hydroxyl group in the more favorable equatorial situation, conformation or place. All right. So that's ribose. So now that we've looked at the conformations of these different carbohydrates, let's take a look at some of the reactions here. And the first one, well, that's not going to do it. I want the line. Let's consider reactions of monosaccharides. There's a couple of common ones, but let's just look at one of them here. This is actually a review. It's pretty bad. I should draw it the proper way here, but we'll just go with that for right now. So let's take our beta glucose again. And imagine what would happen if you were to react this with methyl iodide in excess. So let's think about what the product of that reaction might be. So we have an excess of methyl iodide. And this actually, as I mentioned, goes back to the old days, because now we have this compound with a really good leaving group with iodide. It's a methyl group, so it's not sterically hindered. We have all of these potential nucleophiles here. OH, 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 OH. So you could imagine any one of these hydroxyl groups nucleophilically attacking this methyl group, kicking out the iodide in an SN2-like reaction. So in an SN2 reaction here, we could imagine having our, as I mentioned, our hydroxyl group attack, and then we'd end up deprotonating. So our product here would look something like OCH3, OCH3. It gets a little old here. OCH3, OCH3, and OCH3. And when looking at this, what you'll notice is that all of these groups went from an alcohol, just use this one in the front here, OH, to O-methyl in this case, or OR as a group. So we've ended up forming a whole bunch of ethers. And this actually then is the Williamson ether synthesis. So that's a throwback to OChem 1 for that. And there's other sorts of reagents that one could use that you would react. You'd use an excess as shown here, so like 10 or 100 times of the methyl iodide compared to your sugar. And you're going to, in this case, methylate all of these different hydroxyl groups. Now that's one sort of a reaction, but really a more common reaction shows a slightly different product. And so let's say about formation. Actually, sorry, let's make it just two words. Glycoside formation. This is probably one of the most important reactions with a carbohydrate. So we'll use glucose again in the cyclic form. So same starting material. Now, oh, sorry. I'll scroll up for a second there. See if I can write this here on the bottom. So now as we have our glucose on the bottom here, we're going to react this with methanol in the presence of hydrochloric acid. Now what we would find is that we end up with some sort of a reaction happening, but it's different than above. Now, instead of having every hydroxyl group subjects as an ether, we actually see that we end up with the methyl group in one particular spot. It's just here, OCH3. These are all hydroxyl groups here. This squiggly line doesn't mean anything. That's just, drawing it straight. Get it at an angle. See if I can get it. Plus, we're going to end up with our other stereoisomer. These chair conformations are much worse on the iPad than even on the whiteboard. They're bad enough when I try to draw them in our class. Just haven't got the right angle. Got it. Oh, okay, I'll scroll up now. The reason I have the camera off here too is when I'm writing so you can't see me is because I'm just like hovering over the iPad and twisting it. You can probably hear it moving around as I'm trying to get to the right angle. And this is the result of that. So hopefully you can bear with me, please, for that. And so now what we end up with, again, is we have, this is the alpha, and this is the beta conformation. We end up with both of these. And notice now we just have one methyl group here at the anomeric position. And now we've ended up forming, this is an acetal. So two OR groups. Actually, I should go back a step here to make the difference. This is a hemiacetal. To use more of the language, OH to this carbon, OR, where R is this group here. Now we have OR and then OR. So this is just like what we had before, where we went, say, from aldehyde or ketone to a hemiacetal, OH, OR, to an acetal, OR, OR. Hemiacetal, acetal. So same language, but now in a more complicated structure. So
why
the question
is there only one alcohol that gets changed?
Yeah, it's a great question. So why is it only the one alcohol that gets changed? So why is it that this hydroxyl group seems to be more reactive than all of the others? So that's an excellent point. Let's see if we can come up with a mechanism for that. I'm trying to contain my enthusiasm here. So why only reaction is grammatically incorrect at the anomeric carbon? Okay, let's see if we can figure out the mechanism for this. So let's scribble out, let's try one more attempt here. I need to get a stencil for this. That's even worse, but we'll just roll with it. So we have this same glucose. Now let's consider what happens in the presence of an acid. It happens to be HCl in this case. We could protonate any one of these hydroxyl groups here, the anomeric position, it seems like where the reaction's happening, as well as any of these other hydroxyl groups. And they all will get protonated. Proton comes off, goes on, comes off, all those types of things. But let's see what happens if we protonate that anomeric carbon. So we'll use lone pair of electrons there to protonate. All that we've done is protonated here. This is all the same, so we're just redrawing everything here as the same. Now, what can happen at this position here, at the anomeric position, that cannot happen at any other position, is this oxygen can actually help kick out this group and also stabilize what you end up forming. So this is the key difference, and this is why the reaction can happen here. Let's just draw the two structures. You can imagine these electrons moving in here, kicking out the water, like what we had with our acetal chemistry earlier. And kind of want to get two more structures in here. Let's see if we can make it. Squeeze it in. That's going to give us something that it's a little shaky. Let's try this again. I'll just draw it larger here. It's going to have a double bond at this position. Oh no, there we go. This is all the same. Now we have a formal charge on this oxygen. So now, in this particular case, we've lost water. We formed this species here, which is actually resonance stabilized. So I'm going to scroll up here and draw the resonance structure, where we can imagine these electrons moving up onto this oxygen. Now we have a formal charge on the carbon. All this stuff is unchanged. Okay, let's try that one more time. So what ends up happening here is that when we protonated this anomeric carbon, it's the first step, and create a good leaving group, if that leaves, and you could draw it, actually just have this leave, and you end up down here in the lower right with this carbocation. That carbocation doesn't reside solely on this carbon, but it's actually resonance stabilized by the adjacent oxygen. And that's much more favorable than any of these other positions, because if you protonate, let's assume this hydroxyl group over here, I'm just using this part of the resonance structure, make it a good leaving group, it takes off, you're also with a secondary carbocation. Same thing here, secondary here, and even worse, a primary carbocation here. However, only at this position, when the leaving group leaves, do you have a resonance stabilized carbocation. So it comes back to resonance. So it's resonance stabilized. Okay, and so then the next step is we have this carbocation, we can have our nucleophile methanol attack, and it could attack from the top or the bottom, which is going to give rise to our two different stereoisomers. We'll go this direction now. So we'll have, this is all the same. I'll just use a squiggle to show both stereoisomers. That's actually a legitimate way of showing this. And then in the last step, we could use either Cl minus, or better yet would be using something like water or methanol, doesn't matter which one. It's going to take this proton off. So then our final structure is that glycoside. Squiggle, again, all I've done is take off that proton. And if we used water, we're going to end up with H3O plus. So this is a key reaction with carbohydrates, and actually is a way of linking together different carbohydrates. The observation, as was asked, is that why is it that you only seem to have reaction here, pointing to the top here at the anomeric position? And what makes this carbon different is because it's the one that's adjacent to this oxygen here. It's the one that, as you go to the left from a hemiacetal, to the right here in the reaction to the acetal. And the key thing is when this, going back to I'll go down to the bottom here, when you protonate, turn a bad leaving group to a good leaving group. When that leaving group leaves, you form a resonance stabilized carbocation. And only at that position in the structure can you form that resonance stabilized carbocation, which makes that much more reactive under these conditions. All right, I hope everyone finds that as exciting as I do. I had a few more examples of some carbohydrate chemistry. It ended up going on a little longer than I had anticipated about the exam, but I think that still was time well spent. Why don't we just pause here for 6 minutes? If